Okay, this section we're going to look at nonlinear models. So the logistical model, it basically takes into consideration birth and death. We're going to look at the relative growth rate. Relative pretty much means percent. So it's relative to the population, for example. So that would be dp dt, so the rate of the population with respect to time, over population is our relative growth rate. So we're going to start off with this on the left. And as I said, we're going to include a birth rate and a death rate. And so that formula, it turns out to be where the A is our birth rate and the B is our death rate. So basically dp, the rate of change of the population with respect to time, if I clear my fraction, it's p times a minus bp. And we're just going to call our initial population at time equals 0. We'll call it p naught, some initial population that we can just plug in at a later time. We're going to solve this in general. Now remember, p is our y in other examples. So we have a p squared like a y squared, and what comes to our mind? Well, I don't know about you, but Bernoulli comes to my mind. So we're going to use this method. But we got to set it up in the right form first. So here, the formula for Bernoulli, it's a u sub, not a integrating factor. So it is u equal to, it's p, not y, p to the 1 minus n. Here our n is 2. So our u sub is p 1 minus 2 du in terms of t, it's not x. And we clearly want to solve for dp dt, so we'll just take this and solve for dp dt. There's a minus in there. Minus go to the other side. And this looks like our substitution. And if you remember, we don't change anything else. We'll have what we need if I divide by p squared everywhere, because it showed up in 2 of the terms. And it looks like this is my u. I know it seems like a lot of variables, but try to do this. This is all within your access. So if we just, looks like they're all negative, so I think we can just make them all positive. And now it's set up for integrating factor. So that is mu. So that is mu. Looks like it's a. Sorry, it's not a. My looks like my p of t is a. So it is e to the a dt, which is eat. I love that. So multiply through by our eat, by our integrating factor. This gets written as a product times u, that du becomes u, and it's a beat over here. be to the power of at. It's at this point we want to check, always check your product rule. It's a U, not a mu. Yep, looks like it checks out. So now we can integrate in terms of t. Integrate, it'll be b over a plus our c. Solve for u. Put the c first, and that's a negative at. But u, if you remember, was our p to the minus 1. I have a common denominator. So this is our p of t. Our general solution, we want to use our p of 0 is equal to p naught to find out what that c is in terms of p naught. This goes to 1, so p naught equals, and then we have to solve for that c. Okay, now plugging that c into there, let's go ahead and get rid of the parentheses. And let's get rid of our complex fraction. This will have to go to both of these terms, distribute. Just a note here, as time increases to infinity, what's going to happen? Our p of t, when this goes to infinity, that's that equation, e to the minus a to the t, so that goes to 0. That whole term goes to 0. This whole thing goes to 0. And we basically, the p naughts cancel, we get a over b. And let's look at it going the other way. As t goes to negative infinity, the whole denominator goes to infinity. We can see right here. And so that goes to 0. This is what we have. This is our upper amount. So our graph basically runs along A or B as it goes to infinity. And it goes to 0 somewhere along here. And so somewhere, there's an inflection somewhere. Let me do it prettier. Runs along A or B, goes to 0. There is an inflection point somewhere. This is our 0. So let's look at a little bit of calculus to find our inflection point, if you're interested. So our formula up there, was the rate of the population in terms of time equals AP minus P I think it was p squared, yeah. We distribute it. And if we take our find our second derivative, chain rule, but we can backpedal. dp dt is this, which I'm just going to put that. That's why I did that. So setting these each equal to 0, we have p equals 0. Not a coincidence, that was our lower bound. We have p equals a over b, right there. Not a coincidence, that was our upper bound. And this one, we set that equal to 0. We get p equals a over 2b. I think that's our inflection point. Graphing it. Same graph. And that will be this is our limiting population. It's the upper limit. And you can see here the second half after this hits, growth slows down. And this is our axis P. We have a P naught here. So here's our population models. We have unlimited growth, and this was our last section. We have bounded growth. And basically our U is our constant, our upper bound. It's a constant. There's harvesting. And our H is our harvest constant. Basically, the harvesting is it removes for use. And then this last one that we did was our logistic model. Which is dy dt all over y, which was a minus bp. That's our, remember, that's our birth rate. And actually we should call that y, sorry about that. Up there we use p for population, here we're using y for population. Again, this is our closed population. And this is our relative growth rate. And that's it.